Hi guys, Dr. B here. This is going to be topics 3.10 and 3.11 for AP Chemistry. The objective for 3.10 is to be able to explain the relationship between the solubility of ionic and molecular compounds in aqueous and unaqueous solvents and the intermolecular interactions between particles. So solubility describes the extent to which a solute will dissolve into a solvent to form a solution. So the solute is the thing you're going to try to mix. The solvent is the thing that's going to do the mixing. So like if I put Kool-Aid into a cup of water, my Kool-Aid is a solute, my solvent is the water, the solution is a mixture of both together. If a lot of the solute can dissolve, it can be described as highly soluble. If very little dissolves, it can be described as slightly soluble. And if none can dissolve, it would be insoluble. Water is a common solvent because its ability to dissolve many substances probably helps that it's polar. Water is a good solvent because it's highly polar. It has two sets of lone pairs on the highly electronegative atom, meaning that the electrons are pulled towards, you know that already. The lone pairs give water a bent or angular molecular geometry with a bond angle of 104.5 degrees. When an ionic solid is dissolved into water, the ions become hydrated. Hydration is the process where the water molecules surround the ions to dissolve them. When water molecules surround the ions, they orient themselves so that the partially positive ends of the water molecule are closest to the negative ions, and the partially negative end of the water molecule is closest to the positive ion. This attraction is often referred to as ion dipole, which we saw last couple units ago at least. Water can also dissolve non-ionic substances as well, as seen in the image shown. The water is attracted to the polar part of the acetic acid, the CH3COOH molecule. The OH of the acetic acid is capable of forming a hydrogen bond with the water. This attraction allows acetic acid to dissolve in water. Notice that the acetic acid molecule does not break apart like the ionic compounds. Not all substances can dissolve in water. The memory aid for determining solubility is like dissolves like. This refers to the type of intermolecular forces present in a sample. Substances with similar IMFs to the solvent will dissolve, but if they're not similar, they're unlikely to dissolve. There are three steps that must occur in order for a solution to form. Requires energy, and energy will be released. The solute particles separate, energy is required. The solvent particles must separate, that's energy required as well. And when they come back together, energy is released. The amount of energy needed for each step depends on the IMFs present. The stronger the IMFs, the more energy involved. A polar substance will dissolve into polar solvents, and nonpolar substances will dissolve into nonpolar solvents. They do not dissolve into each other. So nonpolar substance into a polar substance will not dissolve, and vice versa, because there's not enough energy released in the last step to negate the energy needed for the first two steps. When substances can mix together, they're said to be miscible. If they cannot mix together, they are immiscible or immiscible. For each of the following substances, determine the type of IMF present first, and then decide if they will dissolve better in hexane or water. So the formula for hexane is present, C6H14 and water H2O. First, you got to figure out what type of IMFs are present in each for you to decide. So for example, sodium chloride, NaCl, is ionic. C3H8 is a hydrocarbon, so it's all LDFs. CO2, so you have carbon and oxygen, but remember that the structure is, even though it has polar covalent bonds here, overall it's nonpolar. So it's only LDFs. So CH2O, so you have your carbon in the middle, two H's, then your O on the top. So this is going to be dipole-dipole. Hexane only has LDFs, as it is a hydrocarbon, so it's going to be non-polar. Water has hydrogen bonding. Dipole-dipole, and LDFs as well. And it is considered polar. So if I looked at things, C3H8 and CO2 are the only ones that can dissolve in hexane because all of them have nonpolar forces, or they're all nonpolar. I'm sorry, LDFs. NaCl and water can get into ion dipole, and then CH2O, because of its dipole moments, it can interact with H2O. And if you're wondering about the C3H8 and CO2, we'll say no, because we're going to follow the rule that since C3H8 and CO2 only have LDFs, it's most likely not going to interact with the water. I will say though, CO2 does slightly interact and mix. C3H8 does not. So if it's only LDFs, it will not bond with water. It will not mix with water or dissolve with water. So it's saying, actually, it says right here, dissolves better. So the better part is your hint. So that's the way to describe it. Dissolves better, okay? Topic 3.11, spectroscopy and the electromagnetic spectrum. The objective is to be able to explain the relationship between a region of the electromagnetic spectrum and the types of molecular or electronic transitions associated with that region. Spectroscopy is a study of how matter interacts with electromagnetic radiation. Electromagnetic radiation is classified into different types based on its wavelength and frequency. So we did see visible light in chemistry honors, and in physics, depending if it's AP or not, I don't know. I know I taught it in my general physics class about gamma rays, X-rays, infrared, microwave, radio waves, and you'll notice from left to right, as the wavelength gets longer, your frequency gets shorter, meaning that the waves don't appear as often because of the longer wavelength. That's why, just FYI, that's why radio waves can travel from like the antenna at the station to your car, because it travels slower at a less frequency, so there's less energy involved and it gets there, eventually, all that type of stuff. Fun fact, I guess. And also, FM radios stations broadcast in megahertz, and I think AM stations broadcast in kilohertz. So like the number of the radio station is the megahertz, the frequency it broadcasts at. So like now 96.1 broadcasts at 96.1 megahertz. Anyway. Molecular movement. Molecules can move in different ways, kind of a transition here. These can be categorized as translational movement from one place to another, rotational, spinning in place, and vibrational, moving in place. The movement of the atoms within the molecule relative to one another, such as bending, stretching, and all that type of stuff. Vibrational, rotational, translational motions of a carbon dioxide atom, or molecule, are illustrated here. Only a perfect crystalline structure at a absolute zero would exhibit no molecular motion, have zero entropy. In practice, this is unattainable. Same. Anyway, so you'll see what bending looks like. Molecular. So you have bending here. You have symmetric stretching, asymmetric stretching, rotational movement, translational motion. Microwave rotational spectroscopy. Microwave radiation is lower energy than visible light. When the microwave radiation strikes the particles, it causes them to rotate. This is due to the interaction of the dipole of the molecules and interacting with the electromagnetic field of the microwave photons. Key point, microwave radiation is associated with transitions in molecular rotational levels. So the way I think about it is that when you turn on a microwave, what does it do inside? It rotates. So microwave radiation is associated with transition in molecular rotational stuff. Infrared vibrational spectroscopy. Infrared spectroscopy is higher energy than microwaves but less than visible light. It measures the vibration of the atoms and allows determination of functional groups present in a molecule. It analyzes absorption, emission, and reflection. Generally, lighter atoms and stronger bonds tend to vibrate at higher frequencies. Key point, infrared radiation is associated with transition in molecular vibrational levels. So infrared, vibrational, IV, intravenous, whatever, blah, blah. Infrared, vibrational, microwaves, rotate. So if you see something that looks like this, that is vibrational spectroscopy. Let me ask you, what type of motion is associated with this vibration? And they would give you, this right here is associated with an OH. This is a C whatever. This is a CH. They will give you those markers, those types of markers, if you will, for you to identify in another molecule or something. Ultraviolet visible light. So visible light spectroscopy, we can see these colors in the rainbow. The continuum from red to violet, from low to high energy. We've seen this before. The interaction of these wavelengths of the electromagnetic spectrum and molecules or atoms can allow the determination of the concentration of molecules in the solution. The photons of color light are absorbed by a compound, causing electrons to move from their ground state to a higher excited state. By measuring the amount of light leaving what you see from a sample and comparing it to the amount of light that entered the sample, we can find the amount of light that was absorbed by the sample. This is completed using a device called a spectrophotometer. By knowing the amount of light absorbed, one can determine the concentration of a colored substance with a solution. This will be explained in 3.13 Beer-Lambert law. So the key point, ultraviolet visible radiation, it is associated with transitions in electronic energy levels. So when it says electronic, it's talking about electrons. Two samples of copper 2 sulfate were analyzed, and using visible light spectroscopy, sample 1 absorbed twice as much light. So if it absorbs twice as much light, what can you deduce about the concentration of the two solutions? So if one absorbs more light, so to help you all out, this is associated with Beer-Lambert's law. But if we're using visible light spectroscopy, if a sample absorbs more, that means, or twice as much, that means that the concentration of sample 1 is twice that of sample 2. What must be true of the solutions to get results from this type of spectroscopy? Since we're looking at visible light, things you see, your solution, the solution needs to have color. Describe the types of changes that occur within the molecule during the ultraviolet visual spectroscopy. So what's happening here? So the atoms within the molecule absorb energy, which causes the electrons to jump up from their ground state to an excited state. What type of spectroscopy would be responsible from the change of 1s2, 2s2, 2p5 to 1s2, 2s2, 2p6, 2p4, 3s1. So we're looking at electronic changes, electron transitions. So this has to be ultraviolet visible spectroscopy. What type of spectroscopy would be responsible for the bending of OH bonds in water? So when we're talking about bending in bonds in water, we're talking about molecular vibrations. So this will be infrared spectroscopy. All right, gentlemen, that's it for now. That's topics 3.10 and 3.11 for AP Chemistry. Do your best. Hit the like and subscribe. That's the best part. And also If you have any questions, let me know. Okay, thanks. Bye.